Hello and welcome to my presentation, The Sky Isn't the Limit. This recording is done for POUG Conference 2021, so please enjoy. First, I would like to introduce myself. My name is Martin Berger. I'm living in Vienna. I'm with Oracle in the Oracle database area since about 2000. And you can reach me on Twitter. You can send me an email if you have any questions. Sometimes I write blog posts if I find something of interest. I'm also an Oracle ace, which only means I like to talk and write about things. But let's go to the presentation itself. In the next few minutes, I will tell you about two things you should consider. First is the response time, and second is the throughput. In fact, this is true for any system, regardless if it's in the sky, in the cloud, or on your premises, or any mixture of this. It's not even limited to database systems, it's for all systems you might be responsible for. So let's start with this beautiful picture. I was told to show some pictures which should create emotional responses at the audience. And I really hope this creates an emotional response for you. It's not a nice, cute kitty or anything, but as you probably are an IT person or have some mathematical background, this should really create some emotions at you. You can see here there are some X's, but they are not labeled. They have no units, anything, so you have no idea what I'm showing to you here. And I hope this creates something like either some questions or frustration or anger. But we will fix this in a few minutes. This can be a picture you will see if a cloud salesperson comes to you and wants to sell their services. And what they are selling always, if your demand increases, of course, the load on the system increases as well, which is hopefully obvious for you. And at some point, the first system is fully utilized, and the promise in the cloud is you just then provide the next system and the next and so on. And this looks like this. You have the first system, if it's utilized, there are some more up to the limit you need at the moment. You are charged for each and every of them, but you can simply calculate how much money it will cost. Cloud providers promise they can deliver at instance, and everybody is happy. If this is the full story, we could stop here. Unfortunately, there is something more for you in the background. So back to our beautiful picture. We again have the utilization, so more load on the system, and the system raises until a well-defined point. And there are some systems which has really this characteristic. In fact, your customers are not often interested in the system load. They're interested in their response time. And if the response time goes above a certain limit, you have problems because your customers have problems. And on the right side, you see the response time in a system is not linear depending on the demand. When the demand increases on the x-axis here, the response time, or in this case, it's the queuing time, slowly increases. So at 50% of your demand, you only have twice the service time as your response time. But then the bad thing happens. At some point, it really skyrockets and you cannot utilize your system to 100% because the response time will go to more or less to infinite. There are also systems, you can see it on the left side here, which has a constant response time up until it's 100% utilized or close to 100%. And then, of course, it still goes up to infinite. But such a system is more or less perfect for utilization, but it's very, very rare. What I showed you here on the right side is a so-called queuing system. In this case, it's an MM1 queue. We're talking about the queue length. So if there is no load at all, there is no queuing. But if there is more load, more utilization, the queue becomes bigger and bigger. The M stands here for Markovian. The first M is the arrival rate. The second is the time in the service, so how long your service needs to deliver. And the third, the number one here, is the number of so-called servers, so those who can serve, who can do the work. Where do we have this left picture? There are some systems which can deliver this. And a good example for this is a roboter in any manufactory. It really has always the same time to do some work, take it from one side, do the work, and put it on the converter belt on the other side. It's quite simple. And as long as the pieces which need to be done arrive slower, so we don't reach the 100% utilization, as long as they arrive slower than the roboter can work, the time it needs to process is always the same, and we have no queuing. And at the moment, we have more work, the work arrives faster than the robot can process them. The total queuing time goes high immediately, and then the system is overloaded. We never want to reach this. Unfortunately, we can do this in our real world. Most of the time we have such queues. Where do they come from? First, we cannot control our customers the way we can control the converter belt in a manufactory. Sometimes many customers arrive at the same time or close together, and in between we have time where the processor here is idle because no customer is there at all. Still, you have an average over the measurement time over the day or whatever, but the amount of customers in the queue varies based on their arrival. This is meant by the first M here. They are more or less random. We have a second problem here. Our server is not always capable to deliver the same service time. Sometimes he's quite fast, or it is quite fast, whatever it is, and sometimes it takes longer. If your system cannot guarantee a stable service time for each and every demand it has to process, then we have the second M here. The number one says we have only one server. If we have two or three, then those can deliver more services to the queues. Of course, it's faster then. This notation is the so-called Kendall notation. Again, we have the M, and the C, the arrival rate, the service time, and the number of servers. It can also be put in such a graph as the queue and then the service time. The good thing here is if the number of servers increase, the shape here changes a little bit. The more servers we have, the steeper it is at the beginning, and later on it skyrockets. Of course, this has the advantage as long as we have a defined demand of our customer. The more servers we have, the higher we can utilize each system. But the disadvantage is on the other side. At the moment, we increase the load a little bit, then the response time skyrockets immediately, and it's very dissatisfying for our customer. Now let's estimate. We agreed with our customer, we have a queuing time of exactly the service time, so the response time is twice the service time. This is just acceptable. And afterwards, the customer is not satisfied anymore, so we need to do something. Back to the cloud, what do we do then? We buy new servers or new entities of whatever the cloud provider delivers to us and we need for our work. But this has some impacts. Now we have the response time is twice the service time, okay. But this means as we can utilize only 50% of the server afterwards, it's too slow, it's not acceptable for the customer anymore. This nice arrow that cannot go through to the end, but really here at 50% utilization, in this example, we need to bring in new resources. And at the end, this means we have to pay for more servers than on the first picture you might remember. And it's more expensive than calculated or than estimated at the beginning. Of course, it depends where your customer's acceptable response time and queuing time really is. This was the first part. It was about the response time. And you can say, okay, response time now, we see it's about queuing. We cannot control our customers. We can hardly control the service time of our system. So, okay, now I understand the mathematical rules. It's more or less given by God, by mathematics, by whatever. So we cannot do anything about this except we can accept it. And so tell our manager they just need to buy more resources at the cloud provider, and then we're happy. But there is a second thing you need to put into consideration. It's throughput. So it means how many units of work can be done within a given time. Normally it's per second or per minute or per hour or per whatever you are interested in. And here the perfect utilization for a system looks like this. When you increase the number of units in the system, the number of units processed increases as well in the total linear scaling until the system is saturated. Then you still can increase the number of work. It will pile up somewhere, but the units which come out of the other side are still the same highest possible number. This again is a perfect system. And if you have such a system, enjoy. Unfortunately, it looks often more like this. At the beginning, it really goes up, but at some point it becomes slower and slower. So the additional work which can be processed is lower than expected. And you see, we never reach the 100% perfect throughput. It will somewhere always be below this 100%. This depends on your real-life system. I'm quite sure you have seen this before already. So where do we see this? Back, the perfect system is our robot. Each and every piece of work is processed in the same way. They are all totally independent and can be done up to the full utilization of the robot. Afterwards, we can pile up in front of it, but the output is still in the same pace. And you can imagine on the other side, we have our cloud system or our on-premises or whatever you have in your domain and are responsible for. There is a so-called law which describes what we see here. It's called Amdahl's law because this person first described it. And it's about this serialization. So it's about the component we cannot parallelize. One example are logs in the database. And this is just an example as we are here on a database conference. Normally it's such a graphical representation is used. We have a total unit of work. We can divide it in separate parts And most of the parts can be parallelized, can be done at the same time. But a specific part, does not need to be the first or the last. It's just always put for the graphical representation at the beginning or end. This specific part cannot be parallelized. So this is still the serial part of it. And you see here, we cannot, even if we bring infinite resources in the system, we cannot bring it down to only one unit, one length of these squares. We have the first one, the yellow one, which needs to be done serial, and then all the others can be parallelized. And there's a beautiful function for this based on the number of units in the system, the n. We have a factor alpha multiplied by n minus 1. It's the scalability. So each new unit of work in the system at the same time decreases the response, the throughput of the system at the end. This gives us that beautiful curve here. I assume when you ever graphed your response times, you have seen such lines here. Unfortunately, that's still not the end of the story. Beside this, you might even see such a graph. Where does this come from? You can see, say the first thing is your cloud, is your on-premises, but the second one is crying as well. It's raining now. And this one is called the universal scalability law. You can see it as Amdahl's law plus a coherency. So what does coherency mean for us here? The first one, the Amdahl's law, I told you it can be seen as a log in a database. The coherency then means the effort you need to put into your work. When you got the log, you first waited for some resources, then you get the resource and are allowed to do something with it. But before you can do real reasonable work with it, you need to bring it in a shape which is useful for your system, for your specific workload, for your case. So the more different activities are going on in the system, the more dangerous is this coherency. It means someone else changed your data structure, your block, whatever, into something you cannot use now anymore. You can see on the right side the formula for this. The first part is equal to Amdahl's law. It's 1 plus alpha times n minus 1. Okay. The second part really is the one which bites us here. It's the beta times n minus 1. So it's more or less n squared if you ignore this minus 1 part here. So by higher numbers of n, it is really a problem. When you have a look at the graph here, you can more or less say, you can divide it at the top here into a left part and a right part. The left part is dominated by the alpha, but the right part here is dominated by the beta then. You can use this alpha and beta to compare different systems. If you have the same test environment where you can slowly increase the number of the units of work in your system, then you can use the same test case on different test environments, get some points here out, and there are several methods like some Excel sheets or Google Docs or plugins for things like R, the mathematical program R, to calculate this alpha and beta based on real measurements. And with those, then you can really go calculate alpha beta of each and every single system you measure, and at the end compare how they differ. Maybe sometimes you have a lower alpha, and here lower numbers are always better. One system might have a lower alpha and a higher beta in comparison to the other one. And then it depends on your estimated maximal workload. If you see you will hopefully be on the left side of the top of this curve, then it's fine to focus on the alpha. But if you fear you need to utilize your system quite high, then of course you need to have a minimal beta, otherwise the throughput declines again. And that's something you do not want to see if you put more load on the system. I can give you another example. You see this nice Rubik's Cube, and I can, or in the presentation itself, I gave it to the audience, and each one could do some moves with the cube. And of course, I wanted to have the cube back. So until I got it back, this was my waiting time. More or less, they had locks on the cube. They had it in their possession, and I had to wait until the cube was back to me. This was dominated or represented, this would be represented by the alpha then. But at the time I get it back, I want to have it in a specific shape. Let's say I want to have it solved, so I need to do additional work until this cube is correct. And this can be seen as the coherency, the time I need to bring the structure in this coherent way I want to use it. And this is then dependent on the beta here. So we are back to response time and throughput. And I first say to you, okay, response time is something which depends on queuing. You cannot control your customers. They might be random arriving. You probably cannot control your service time to make it persistent. So you have this dangerous curve. And you cannot do a lot of this. You, of course, want to have a lot of customers. So you need to go to your boss and tell him or to buy sufficient resources. But throughput is something totally different here. First, you need always to see them as different things, even they are related, but there is no linear relation between them. So please observe them independent. But throughput is something your system can change, or you can change it in your system. If you make it work with less locks of data structures, you reduce the alpha. If you use better data structures which do not change, you reduce the beta part of the universal scalability law. So the further you improve your system, it helps the response time as well, because it will be faster. This is normal tuning. So the service time is smaller, and you can put more users on the system until the maximum response time is reached. But you get more direct input to the throughput, the lesser the locking is, the lesser the coherence is, the better for you. You will never get these numbers down to zero. They're just artificial environments where you can bring it to zero. One is the robot that we talked about before. And there the trick is, it just does exactly the same thing every time. There is no variance, or the variance in all this work is so small that it's covered in all the activity. The second part, this robot is never used at its maximum possible speed, because then you have variance automatically. If it's warmer or colder, then it can move faster, slower, anything. So it's not used at its maximum speed. This is the second part. And the third, the arrival is really managed exactly to the speed the robot can work at. So it's artificially put below its optimum or maximum speed. And this delivers the same, the constant throughput, and of course the constant service time. The robot is also independent from other robots which are doing the same thing. One example for you would be a farm of random number generators. Each and every of these number generators is totally independent of the others, otherwise it would not be totally random. So if you need more random numbers, you can just bring up a new server which just generate them as well. They're independent, and there it scales perfectly well for you if you put the correct algorithm to generate random numbers. So as this is only recorded, I'm quite fast here, no interaction with my audience, which is very sad. So I can only tell you again, if you have any questions, please contact me at Twitter, send me an email. I will really try to respond with all your questions. The last thing I can give you here is more additional literature. My goal was not to give you all the mathematics in the background, not the Excel sheets or the R models or whatever. Just to tell you, there is response time, there is throughput, and they are never that perfect as maybe a salesperson wants to tell you. So beware of it and be prepared. It will bite you at some time, and if you know about them, it's better. And it's even more better if you know about the mathematics behind. And for this, I can tell you about these two books. The first one, Forecasting Oracle Performance, was my, let's call it, initial drug on this area. So this is something I read from the DBA perspective, and it helped me to understand what's going on and gave me the initial mathematical background for this. Of course, it is only a beginner from the methodical background. It raised additional questions, and the next book I took then was Guerrilla Capacity Planning. A lot of funny things are explained there, and this was my way through the learning curve. If you're interested, either start your Google and search for whatever you're interested for, or send me an email and ask me questions, or you can search for these books or whatever you prefer otherwise. I'm really thankful for your time. I hope it helped you anything. Please give me some response if you're interested in anything. Otherwise, thank you for joining this.